Hello, and welcome to Right Triangle Trigonometry. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas, El Paso, and an assistant professor at Doniana Community College. This lecture is for Math 1508 Pre-Calculus at UTEP, but I'm sure it applies to other people too. We use Larson's 10th edition Pre-Calculus text. This is Chapter 4, Trigonometry, Section 4.3, Right Triangle Trigonometry. So, finally we get to measure some triangles instead of just talking about angles. And the second way that the six trig functions can be defined is through a right triangle. The first one being the unit circle, which is very valuable. A right triangle is a triangle with a right angle 90-degree angle. So a 90-degree angle, across from that is the hypotenuse. For either of the other two angles, let's take this one. If this angle is x, I say this is the side adjacent, and it's not just me, everybody. Side adjacent touches both the angle and the right angle, whereas for the angle x, always in reference to the angle, this is the side opposite. However, if I were to look at this angle x, now this would be the opposite, and this would be the adjacent. So it all depends on the reference. Where are you looking from? For an angle x here, this is adjacent. For the angle x here, this side is adjacent. So pay attention to where you are. So if theta is an acute angle of a right triangle, meaning it's not the 90-degree angle, the six trigonometric functions of the angle theta are defined as follows. Sine of theta is opposite over hypotenuse. The cosine is adjacent over hypotenuse. A tangent is opposite over adjacent. And then we flip them over, right? Just like we did before with the unit circle, cotangent is the reciprocal of tangent. Secant is the reciprocal of cosine. Cosecant is the reciprocal of sine. Op, adj, and hyp, of course, are the length of the opposite side, length of the adjacent side, and the length of the hypotenuse. One way that students choose to remember right triangle definitions is through something called SOHCAHTOA. Sine is opposite over hypotenuse, SOH. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. And the pronunciation guide is SOHC. So SOHCAHTOA. SOHCAHTOA. And another visual of it, using the full words opposite and hypotenuse, and the visual of the triangle. Pause here if you need to, so you can write it down, make sure you get everything you need. Again, here, if I go vertically instead, I have sine, cosine, tangent. I would work my way back up with cotangent, secant, and cosecant, doing reciprocals of the ones across. So, let's find the exact values of the six trigonometric functions of the angle theta. And we're given one leg is a 5, the hypotenuse is 13, and the 5 is the opposite side. So in order to find the exact values of the six trig functions, I have to know the lengths of all three sides. But the great thing is Pythagoras. The Pythagorean theorem works for every right triangle. So I know that 5 squared plus x squared equals 13 squared. And I know 5 squared is 25 and 13 squared is 169. So when I subtract, I get x squared equals 144. And the square root of 144 is 12. So I know that my x value is 12. Now, normally when we take a square root, we have to consider both plus and minus. But this is a physical triangle. It is not going to have a length of negative 12. We don't need direction in this. So it's just the principal square root as we're solving. Now, in reference to theta, sine is opposite over hypotenuse, 5/13. In reference to theta, cosine is adjacent, 12 over 13. Tangent is opposite over adjacent, 5/12. Then cotangent flips over tangent, secant flips over cosine, and cosecant flips over sine. If I'm given a triangle with opposite side 6, adjacent side 8, and I want to find the hypotenuse, then the Pythagorean theorem says 6 squared plus 8 squared equals h squared. 36 and 64 makes 100, so my hypotenuse has a length of 10. In reference to theta, sine is opposite 6 over hypotenuse 10, 6/10, which simplifies to 3/5. In reference to theta, cosine is adjacent over hypotenuse 8/10, which is 4/5. In reference to theta, tangent is opposite over adjacent, so that's 6/8, which simplifies to 3/4. I'm going to use all these simplified values and work my way back up. The cotangent is 4/3, the secant is 5/4, and the cosecant, the reciprocal of sine, is 5/3. If you know the big three, the other three are easy. Here we're given an isosceles triangle, isosceles right triangle. Theta, the side adjacent and the side opposite are both 4. So 4 squared plus 4 squared equals 8 squared. 16 and 16 makes 32. And the largest perfect square that goes into 32 is 16. So I could rewrite square root of 32 as the square root of 16 times 2. I know the square root of 16 is 4, and so do you. The square root of 2, don't know. So the square root of 32 can be simplified to be 4 square root of 2. I encourage you to always simplify your radical first. It's going to make these calculations easier. Simplify once to make 6 things easier, or be lazy here and have work to do in these 6. So always, I'm a big fan of being lazy, but be lazy later, not early on. So the sine in reference to theta is opposite over hypotenuse. 4 over 4 square root of 2 simplifies to 1 over square root of 2, and when I rationalize my denominator, I get square root of 2 over 2. In reference to theta, cosine is adjacent, 4 over hypotenuse, 4 over 4 square root of 2, and I just did that operation, so I'm just going to write the solution. In reference to theta, tangent is opposite, 4 over adjacent, 4. 4 over 4 is 1. And then I flip them over. Cotangent of theta, the reciprocal of 1 is 1. I wrote these top down, but I think of them bottom up. If I flip over square root of 2 over 2, I have more work to do. So I like the simplified version here. If I flip over 1 over square root of 2, take the reciprocal, that's just the square root of 2. These sine and cosine are the same, so secant and cosecant are the same, the square root of 2. Now if I'm given cosine of theta equals 1/3, I want to find the values of sine, tangent, and secant. This cosine theta equals 1/3 allows me to set up a right triangle. We're going to assume I can draw a right triangle freehand. Not always a good assumption. And I'm going to put theta here. In reference to theta, cosine is adjacent 1 over hypotenuse 3. That's exactly what we have, right? Cosine is adjacent over hypotenuse. It tells me my adjacent is 1, my hypotenuse is 3. Now I can find my y value using the Pythagorean theorem. 3 squared minus 1 squared makes 8. If 8 equals y squared, then y is the square root of 8. 8 is 4 times 2, so that's the square root of 4 times the square root of 2. We call that 2 square root of 2. Using our y value of 2 square root of 2, I want to find sine. In reference to theta, sine is opposite over hypotenuse, 2 square root of 2 over 3. Tangent, in reference to theta, is opposite over adjacent, so 2 square root of 2 over 1, which is 2 square root of 2. And secant is the reciprocal of cosine. Well, I'm given cosine, that's 1/3. The reciprocal is 3. I didn't need to find y in order to find the secant. But if I wanted to, I remember, secant is also hypotenuse over adjacent. Hypotenuse is 3, adjacent is 1. 3 over 1 is 3. We talked about some special angles in the unit circle lecture, and 0 along with 90 degrees, or 0 and pi over 2 were added to this list. But the reason that we call these special angles in the right triangle section is that if we have a poorly drawn circle, not even a circle, that's a really bad drawn circle, that's a triangle. If we have a 30-degree angle and a 60-degree angle, we call this a 30, 60, 90 triangle. It just so happens that a side length of 1, a hypotenuse of 2, and a side length of the square root of 3. If you memorize this triangle, it's the same as memorizing 30, 60, 90 degrees for your unit circle. If you prefer, you could do a nice isosceles right triangle. This is similar to the example that had 4s for both legs. This is 45 degrees. This is 45 degrees. And this is 90 degrees. If you memorize this triangle, you have this line all worked out for you. Not rationalized, of course. 1 over square root of 2. When I rationalize the denominator, I'll get square root of 2 over 2 for both sine and cosine. That's a 5. It looks like a 1. I've squared it's a 5. My pen's not top of the line, but, you know, it's a great start. So these are great things to memorize, and if the triangles help you memorize them, maybe the triangles are easier for you than the unit circle, well then these two triangles can help you memorize that unit circle, which will be very valuable down the road. We have some fundamental trig identities, and we've already used these. We talked about how sine and cosecant are reciprocals of each other. Cosine and secant, reciprocals of each other. Tangent and cotangent, reciprocals of each other. Notice that a co-function, cosine for example, its reciprocal does not have a co. So there's one function and a co-function. One function and a co-function, always. Never two co-functions make reciprocals, never two together. We've also looked at quotient identities in the unit circle. We define tangent as being y over x, where sine of theta was equal to y and cosine of theta was equal to x. So it's the same thing here. The tangent is the quotient of sine of theta divided by cosine of theta. Cotangent is the reciprocal, right? It's the reciprocal. So flip it over. That'll be cosine of theta over sine of theta. The way I remember it, cotangent of theta starts with cosine of theta. Whatever works for you. We also have some Pythagorean identities. We have our unit circle. And a unit circle is a circle centered at the origin, so x squared plus y squared, with a radius of 1. This comes back to us from algebra. And in the unit circle, we defined a sine of theta to be y and cosine of theta to be x. And of course, I have these written in the opposite order of my x and y, but I'm adding, so it's okay. So from the unit circle, we know that sine squared of theta plus cosine squared of theta equals 1. Let me throw down another note on notation. The sine of theta, all squared, is written as the sine squared of theta. The reason for this is we don't want the squared to just be on the angle. So we don't want to square the angle, we want to square the sine of the angle. So this is the standard notation. If you see sine squared of theta, what it really means is sine of theta times sine of theta. I'm not squaring theta, I'm not squaring sin, I'm squaring the sine of theta. So sine of theta squared, sine squared theta. But if I divide everything by a sine squared, so sine squared divided by sine squared is 1. Cosine squared theta divided by sine squared theta is cotangent squared theta. And 1 divided by sine squared theta is cosecant squared theta. So from the basic unit circle, in terms of sine and cosine, I have a second Pythagorean identity. And it comes from right triangles. If we divide this original function by cosine squared, sine squared theta divided by cosine squared theta is tangent squared theta. Cosine squared theta divided by cosine squared theta is 1. And 1 divided by cosine squared theta is secant squared theta. So we have our 3 Pythagorean identities. If you know this one, which truly is the easiest one to memorize, you can find these two. I will preview a little bit. This is pre-calculus, a preview of what's coming in calculus. The stuff you need to know. Cotangent and cosecant, they're always going to be buddies. They're going to stick together in a lot of things we do with derivatives and integrals and that sort. Tangent and secant also stick together. Sine and cosine, they're the building blocks of everything else we do. Sine and cosine always stick together. And then the co-functions, tangent and secant. Alright, so we're going to see this several times in this lecture series. It's just because it's really helpful and important when it comes to calculus and just simplifying in general. So use the trig identities to transform the left side, which I call LHS, because I'm far too lazy to type out 8 letters and a space when I could use 3 letters. We're going to transform the left-hand side of the equation into the right-hand side of the equation. So if we're given cosine theta times secant of theta equals 1, our left-hand side is cosine theta times secant of theta. Well, there's not much I could do, but I do know that secant of theta is 1 over cosine of theta. Oh, look at that. If I want to multiply cosine of theta times 1 over cosine of theta, I could put a denominator of 1 to make two fractions, multiply straight across. I'll get cosine theta over cosine theta, but guess what? Cosine of theta divided by itself is 1. My right-hand side, I've simplified it. So basically, these instructions are saying, hey, start with the left side, give me all the work that shows me that it's the same as the right-hand side. Tangent of alpha times the cosine of alpha equals the sine of alpha. So my left-hand side, tangent of alpha, cosine of alpha. Well, when all else fails, take it to sine and cosine. I know that tangent of alpha is sine of alpha over cosine of alpha by the quotient identities. If you Google my name, Tuesday Johnson, you can throw the J in there if you want to, and Google fundamental identities, possibly it'll show up. I think random trig handouts is a great one with my name at UTEP, and you can go to my website and you can find just random trig handouts, really, and the identities that were on the previous slides are somewhere on that handout, along with a copy of the unit circle if you're interested. But it's nice to have those next to you until you get them completely memorized. So I replace tangent of alpha with sine of alpha over cosine of alpha. When I have two functions or two fractions being multiplied, I multiply the numerators, I multiply the denominators. But look at that. Cosine of alpha is going to cancel, and I'm left with the right-hand side, sine of alpha. If I have secant of theta plus tangent of theta times secant of theta minus tangent of theta, I want to show that that equals 1. So my left-hand side, I'm going to multiply that sucker out. Using FOIL, right? Secant of theta times secant of theta is secant squared of theta. Secant of theta times minus tangent of theta is minus secant theta tangent theta. Here I'll have a tangent theta, secant theta, and finally a minus tangent squared theta. Alright, but look, tangent theta, secant theta, and a negative tangent theta, secant theta, it's multiplication. I could go and it's commutative, it's all good. So these two cancel out. I'm left with secant squared theta minus tangent squared theta. But when I'm thinking squares, I naturally go to Pythagorean identities. And I know that secant squared of theta is the same as 1 plus tangent squared of theta. Go back to your Pythagorean identities, check it out. Right, there it is. I'm right. 1 plus tangent squared theta minus tangent squared theta. Now these two cancel out and I get my right-hand side of 1. If you don't feel like multiplying these out, you could notice that this is the formula for factoring the difference of squares and jump straight to here, and you'd be good to go, but you still need to use a little Pythagorean identity. It doesn't have to be this. You could have solved for tangent squared theta and substituted there, maybe a step or two more. Many different ways to get these transformations complete. Sine squared theta minus cosine squared theta equals 2 sine squared theta minus 1. Now, when you're not sure what to do with the left-hand side, use the right-hand side as your guide. I see that the right-hand side still has sine of theta. So I'm going to replace cosine squared theta. I know that sine squared theta plus cosine squared theta equals 1. So if I subtract sine squared theta from both sides, I know that cosine squared theta is 1 minus sine squared theta. Because there's a negative in front of it, I use parentheses. So I remember to distribute my negative. And what do I have here? I have 2 sine squared thetas minus 1, my right-hand side. So if you're not sure how to start, you're already on sine and cosine, use the right-hand side as a guide. Alright, so there are so many different ways to transform these. And I could have 10 students do this one problem, and they could all do it a different way, and they could all be completely correct. So don't get locked in on, oh, why'd she do that? How'd she do that? Try these on your own. See if you can find another way. Just make sure all your substitutions are correct, and it's all good. I'm going to start with tangent of beta plus cotangent of beta, all divided by tangent of beta. And I want to show that that's equal to cosecant squared of beta. Why? Isn't it nice to have motivation? This ugly, it's a fraction that involves two different trig functions, right? Tangent and cotangent. Wouldn't it be nice if instead of dealing with a fraction with two different trig functions, I could just square one trig function? It's nice to be able to simplify. Instead of transform, we'll later call this simplify, or verify the identity. It's nice to be able to deal with something smaller, something easier, and especially when it comes to calculus. So that's the motivation for this skill. Tangent of beta plus cotangent of beta over tangent of beta. If I were to give you tangent of beta over tangent of beta plus cotangent of beta over tangent of beta, you could see the common denominator, and so you would add the numerators and go to the left. But don't forget, we can also pull it apart. So a denominator of tangent of beta can be given to each term of the numerator. Then I'll have tangent of beta over tangent of beta is 1. Also, dividing by tangent of beta is the same as multiplying by 1 over tangent of beta. Let's put it in things that we can think about. Dividing by 2 is the same as multiplying by a half. Very important little mathematical technique here. Rewrite division as a form of multiplication. Because I know the reciprocal of tangent is cotangent. I know that cotangent of beta times cotangent of beta is cotangent squared of beta. I see a square, I see a 1. I go back to my Pythagorean identities and look at that. Yep, we got exactly what we needed, the right-hand side. Alright, let's do a few word problems now. You're skiing down a mountain with a vertical height of 1,500 feet. The distance from the top of the mountain to the base is 3,000 feet. What is the angle of elevation from the base to the top? So I want to know this angle here. Angle of elevation, if you're looking straight out, angle of elevation, you'll look up. Whereas angle of depression or angle of declination, you'll look down. So in reference to this angle, all right, what is the angle of elevation? What is theta? In reference to theta, I have opposite and I have hypotenuse. So it must be that I'm using sine. Sine of theta is 1,500 over 3,000, which is a half. And it's one that you should have memorized. Sine of theta equals 1/2. You could go back to the table we had earlier in this lecture, or consult your unit circle. Sine of theta equals a half when theta is 30 degrees. 30 degrees is just something for us to visualize it. The real number answer would be pi over 6. A guy wire, did you know that that's what they were called, guy wires? A guy wire runs from the ground to a cell tower. The wire is attached 150 feet above the ground to the cell tower. The angle formed between the ground and the wire, is 43 degrees. I want to find how long is the wire, and I want to know how far away from the tower is it attached to the ground. So the visualization of the situation can be made into a nice basic right triangle. A height of 150. I don't know the length of the wire. I don't know the distance on the ground, but I do know this angle between the ground and the wire is 43 degrees. Let's see what we can do. So, for the guy wire, I have 150, the wire, and 43 degrees. What am I given in reference to the angle? I'm given the opposite and the hypotenuse. I have no idea what that value is right there, but it's not part of this problem that I can think of. Opposite and hypotenuse, so I'm using sine. Sine of 43 degrees is 150 over w, my hypotenuse. So let's multiply both sides by w. Divide by the sine of 43 degrees. Now, when you put this in your calculator, and I've told you several times now in this series that you should always use radians for your calculations. Unless you're in this situation, in which case you could put your calculator in degree mode, or you could leave your calculator in radian mode, use the angle menu in order to use the degree symbol. 150 divided by the sine of 43 degrees is 219.94. So about 220 feet is the length of the wire. Calculators can do calculations in degrees. Humans cannot. Right? Calculators convert it and do all sorts of fancy things really fast. We don't. So how far from the base of the tower is the guy wire attached to the ground? Wow, try to save that really fast. So I have 150 feet up the tower. I have the ground. I have my 43 degrees. So in relation to the 43 degrees, I have opposite and adjacent. Well, opposite and adjacent tells me I'm going to use tangent. The tangent of 43 degrees is opposite 150 over adjacent g. Multiply both sides by g and divide by the tangent of 43 degrees. When I enter this in my calculator, either in the correct mode or remembering my degree symbol, I'll get 160.85 feet. Pay attention to your homework exercises or your exams where it tells you how to round, how many decimal places. I go with a standard of 2 if the directions don't say anything. I really should, if I'm using WebAssign and the directions do not state, I should go with an exact value. But I do a tendency of, this is a real life application. I'm not going to tell somebody, hey, make sure that's 150 divided by tangent of 43 degrees away from the base of the tower. They're going to look at me like maybe I need to go do a urinalysis to make sure I should be on the job. So we estimate the values when it's a real life situation. Decimal places, great idea. Alright, can't leave out you biologists. A biologist wants to know the width of a river so that instruments for studying the pollutants in the water can be set properly. I'm right here next to the Rio Grande, and trust me, we have pollutants. So from a point A along the shore, the biologist walks 100 feet downstream and sights to a point C. This point C is right across the riverbank from point A. It's determined from this sighting that the angle B, from A to C, so we call it angle B, is 54 degrees. I want to know, how wide is the river? Well, I have 100. This is adjacent to my B value, my angle. I want to know the width of the river. That's the opposite side. I don't really care about the hypotenuse at all, so I'm going to use tangent. The tangent of 54 degrees is W over 100. To get the width of the river by itself, I multiply both sides by 100. Using the appropriate mode in my calculator, or the degree symbol if you want to stay in radian mode, I find that this particular river in a made-up world is 137.6 feet wide. This will allow me to spread out my instruments for detecting pollutants or whatever it is I need to do. Now, as to how you're going to get those instruments in the river, probably time to get wet. Anyway, that's right triangle trigonometry. Thanks for listening.